Okay, let's take a look at calculate entropy. Entropy S is equal to Q reversible divided by temperature Kelvin. And we're looking at the change in entropy. So ice, of course, does melt, okay, at a temperature of 0 Celsius or 273 Kelvin. So if we want to take a look at the change in entropy for this, we know the latent heat for this is 334, and that would be kilojoules, okay, per kilogram. That's how it works. And probably in chemistry, you would be measuring that in kilojoules per mole, but here we are in physics, so we use kilograms. So then if I want to calculate this Q reversible, I would take 334, and that's kilojoules per kilogram. And of course, I'm going to divide that by 273 Kelvin. So we're left with the number of kilojoules per kilogram, and then Kelvin is also on the bottom. And again, in chemistry, it's like kilojoules mole Kelvin on the bottom. Okay, so there you go. Now, what if we consider melting ice at a higher temperature? Let's say we change the temperature equal to 373 Kelvin. Well, then I'll take 334 kilojoules over kilograms, and I will divide that by 373 Kelvin. What we're noticing then that the change in entropy is now less than it would be if we did it at 0 Celsius or 273 Kelvin. And the reason for that is the universe at a higher temperature is already more chaotic. Molecules are moving faster around there. So it's not going to notice that as much of an increase in entropy because we're already pretty chaotic. And I made an analogy in the classroom. You know, said if everyone's sitting in the chair and we're really quiet, okay, and really ordered, when someone comes in and gives me a pass that disturbs you a lot, you're going to notice a lot more chaos at that moment. But if you're in a lab situation, everyone's already moving around their desks, and someone comes in with a pass, then you're probably not going to notice that because there's already a lot more chaos going on in the room because you're in a lab. So the universe is just like that. At a more ordered temperature of 273 Kelvin, when solid goes to liquid, the universe notices that it's more increase in entropy than if it was already in a more chaotic situation at a higher temperature. So it kind of works the same. So it's kind of an analogy there for you. Okay, now what about thermal conductivity? So if I have a hot object here, this at T2, and a cold object here at T1, and I've got an insulating barrier between the two, we're going to notice that this is an application of the zeroth law of thermodynamics. Heat will flow from the warmed object to the cold object until they're both at the same value of their temperature. But what's that related to? Well, we have an equation that looks like this. The power, energy rate transfer, is equal to the thermal conductivity constant K, okay, multiplied by the cross-sectional area, divided by the distance between the objects, and this is all multiplied by the temperature change, T2 minus T1. So if we just take a quick look at this equation, K, of course, is a unique constant to the barrier. How well does it allow energy to travel through? The larger the surface area, the more energy that can transfer through. And the greater the distance between the objects, it's going to take a longer time for energy to go through. And of course, the temperature difference, something really hot to something cold, is going to transfer more heat than something that's pretty close in temperature. So now the unit for this is actually power, so it is in watts, so it's a rate of energy transfer. Now remember, watt is also the same thing as a joule per second. So this is a rate, okay, of energy transferring across, okay, as the temperatures go to equilibrium. So I would expect that rate would drop as the temperatures get closer to each other. Okay, and that's our thermodynamics, and our next videos will be on something different, and good luck studying.